Okay, this is project test number 4, video 3, questions 21 to 30. Data on homes recently sold in a certain town included the area of the home reported in square feet. The table below shows the summary statistics of the reported areas in square feet. So we have a mean, the minimum, the first quartile, the median, the third quartile, the maximum, and standard deviation. An auditor determined that an error was made in the reported areas and that all the areas should have been 100 square feet greater than was reported. So they should go back and add 100 to every single value. The areas were corrected and new summary statistics were reported. What were the interquartile range and the standard deviation of the corrected areas? So first off, we're adding a constant to every single value. If we add a constant, the mean will shift by 100. The minimum will shift by 100. Q1 will shift by 100. The median will shift by 100. Q3 will shift by 100, and the maximum will shift by 100. So all those values will shift by 100. However, measures of spread will not change. So our IQR and our standard deviation are not going to change. They're going to remain the same. So our standard deviation is going to be 61,000, which is what we have right here. And we need to calculate our IQR. IQR is just Q3 minus Q1, which in this case, 1,806 minus 1,704. We subtract those two and we get an IQR of 102. Okay, the measures of center shifted or would have shifted by 100, but the measures of spread would not have changed. All right, and that's what they were testing you on right there. So that's 21. All right, number 22, a two-sample t-test for the hypothesis mu1 minus mu2 equals 0. In other words, no difference. And mu1 minus mu2 is greater than 0, produces a p-value of 0.03. Which of the following must be true? And they start talking about a confidence interval. Well, here we have a one-tailed test with a p-value of 0.03. So we end up with a p-value of 0.03, but that was for a one-tailed test. All confidence intervals are two-tailed tests, so we have an additional 0.03 in the center, which means we only have 0.94 because these have to sum up to 1. Now, to be statistically significant, you cannot contain 0. So the largest interval that won't contain 0 is 0.94. All other intervals do. Well, that means 0.95 will contain 0 and 99 will contain 0. This one will not contain 0. So the 90% confidence interval would not have contained 0 and would appear to be statistically significant, but the 95 and 99 would have contained 0. So our answer choice is D. And once again, we had a one-tailed test of 0.03. We went to a two-tailed test, so our p-value doubles. So one-tail to two-tail, the p-value doubles. All right, 23. A medical doctor uses a diagnostic test to determine whether a patient has arthritis. A treatment will be prescribed only if the doctor thinks the patient has arthritis. The situation is similar to using a null and alternative hypothesis to decide whether to prescribe the treatment. The hypothesis might be stated as follows. The null, the patient does not have. So this is a does not. And this one, the patient, the alternative is that they do. Which of the following represents a type 2 error? Remember, type 2 is fail to reject. All right, in error. In other words, you made a mistake. So We believe HO, but it is false. HA is true. All right, so that's a type 2 error. We believe HO, but it's false. HA is true. So which represents a type 2? Diagnosing arthritis in a patient who has arthritis. First off, diagnosing that they have arthritis, that's a correct decision. We're not even worried about correct decisions. We're worried about errors. So that's not even an error. Failing to diagnose arthritis in a patient who has arthritis. We believe they don't have arthritis when in fact they do. All right, believe HO, believe they don't have it, but they do. That is a type 2. All right, so 23 is B. 24, a biologist wants to estimate the difference between the mean body lengths of green and brown stink bugs. Sure they do. A random sample of 20 green stink bugs has a mean body length of 16.22 and a standard deviation of 1.34. A random sample of 20 brown stink bugs has a mean length of 13.41 and a standard deviation of 0.73. What is the standard error of the difference? All right, so they're just trying to upset you a little bit. So here's the equation. T equals x bar 1 minus x bar 2 over S1 squared N1 plus S2 squared N2. Let's plug into that equation. All right, they want to go green minus brown. And 16.22 versus minus 13.41. And both of them had the same sample size. We had samples of size 20. And this one had 1.34. And this one is 0.73 squared. All right, our standard error is this part right here. Be really, really careful. I know you know how to do this, but it's so easy to rush and go, yay, I see the answer, and you be wrong. All right, so 1.34 squared plus 0.73 squared. Remember, when we add fractions, we don't change the denominator. So this stays 20. Remember, 2/5 plus 1/5 equals 3/5. The denominator doesn't change, so it stays at 20. So 1.34 squared plus 0.73 squared, 24 is C. "25, a blind taste test will be conducted with 9 volunteers to determine whether people can taste a difference between bottled water and tap water. Each participant will taste the water from 2 different glasses and then identify which glass he or she thinks contains the tap water. Assuming that people cannot taste the difference between bottled water and tap, what's the probability that at least 8 of the 9 will correctly identify the tap water?" So first off, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the values we're interested in. We need to figure out the probability. But it says that they cannot taste a difference, which means they're equally likely to choose one or the other. If you're equally likely, that means your probability is 0.50. It's like flipping a coin. So we have a fixed probability, a set number of trials. This makes this the binomial. All right. And because we have multiple values, this makes it a binomial CDF. And since they used at least, we probably want to use the 1 minus. So 1 minus the binom CDF trials, we have 9 trials. Probability 0.5. We're going to subtract out the largest value we don't want, which is 7. Now, if I were showing my work on a test, I would make it the sum of the two PDFs, which would have been 9, choose 8, 0.5 to the 8th, 0.5, 9 minus 8 is 1, plus 9, choose 9, 0.5 to the 9th, 0.5, 9 minus 9 is 0. So on the calculator, this would be what I was doing on an FRQ. On a multiple choice, I do not need to show my work. So 1 minus second vars, binomial, CDF, trials is 9, probability is 0.5, X value is 7. And I get 0.0195. My X value is 7 is I wanted 8, so I subtract out the highest thing I don't want. The highest thing I don't want is the 7. All right? Number 26, a school administrator is interested in estimating the proportion of students in the district who participate in community service activities. From a random sample of 100 students in the district, the administrator will construct a 99% confidence interval for the proportion of all district students who participate in community service activities. Which of the statements must be true? All right, so we're constructing a 99% confidence interval, which means in repeated sampling, we expect to capture it 99% of the time. Or if we did this over and over and over, that also means if we did it over and over again, 99% of the time we capture it. It also means we are 99% confident that we captured the true population proportion. So the proportion will be in the confidence interval. That would be nice, but we're not 100% sure of that. We're 99% confident that it'll be in there, but we're not 100%. Here they use the word probability. They should not have done that. So we're going to come back to this one in just a moment. I fault them on this because they use probabilities on these and they should not have. The probability that the confidence interval will include the proportion is 0.99. That's probably not it, but we're going to mark it anyway as a possibility. The probability the confidence interval will include the sample proportion is 0.99. First off, we never talk about the sample proportion, and if they were going to do, it should have been 100% because it will be in there in the middle 100% of the time. That's a guarantee. D, the population proportion and the sample proportion will be equal. That would be nice, but our sample proportion is only an estimate, not likely to be equal. No guarantee of that. The probability the population proportion and sample proportion will be equal is 0.99. Okay, even though they use probability, this is our best answer. This should have said, we are 99% confident that the interval will include the population proportion. This is the only time I've ever seen this, and this violates what. So don't like this problem, but it is what it is. 27. 3 brands of candy, X, Y, and Z, are made many colors. Shado produced 1 bag of each brand and counted the number of pieces of each color. By the way, we don't know how many candies are in each bag. We just know the proportions. The graph below shows the relative frequency distribution of the colors in each bag. But we don't know if brand X has 1,000 pieces, the brand Z has 10. All we know is these are the proportions, but we don't know how many are in each one. All right, be careful with that. So for which must the statements be true? For brand X, there are more green candies than there are red candies. Well, these are the green candies, and it's not quite 2, and this is 2, so that's false. There are more red candies. Brand X has more red candies than it does green candies. For brand Y, looking at brand Y, which there are more red candies than there are green pieces. And I look at this is more than 2, and this is less than 2. This is a true statement. B is my answer to number 27. Number 28. A large newspaper periodically reports the mean cost of dinner for two people at restaurants in the city. The newspaper staff will collect data from a random sample of restaurants in the city and estimate the mean price using a 90% confidence interval. And mean price. In past years, the standard deviation has always been very close to 35. Assuming the population standard deviation is 35, so they're now telling us, hey, let's believe that it's 35. Which of the following is the minimum sample size needed to obtain a margin of error of no more than $5? So we're going to have X bar plus or minus Z star, and it's a Z because we're using the standard deviation of the population. Standard deviation divided by the square root of n. This part equals the margin of error. They told us the margin of error can be no more than 5. They told us the standard deviation is 35. We know we're looking for n, so we need to go calculate our Z star. So second vars, inverse norm, parenthesis, 1 minus 0.90 because it's a 90%, divided by 2, mean is 0, standard deviation of 1, and we're going to get 1.645. I'm going to go ahead and multiply that by 35. 1.645 times 35 equals 57.575 over the square root of n equals 5. I'm going to do a little bit of algebraic manipulation when multiply both sides by the square root of n. So now I have 57.575 equals 5 square roots of n. Divide both sides by 5. And I want to get rid of the square root, so I'm going to raise everything to the second power. So here we go, 57.575 divided by 5, press enter. Then I'm going to square it. And I end up getting 132.59. And we always, regardless of the decimal, must round up. So n needs to be about 133. And they gave us this answer choice. So our answer choice is C, right? Number 29. A field researcher who studies lions, that seems safe, conjectured that the more time a cub spends playing, the sooner the cub will begin to hunt. Observational studies were collected with 20 lion cubs. The researcher recorded how long they spend playing and the age when they began hunting. Because male and female lions have different hunting behaviors, the researcher recorded the data for males and females separately. The two scatter plots show the data for the 10 female lions and the 10 male lions. And if I were drawing a regression line, my regression line for the females would look something like this. And I don't know if that's right or wrong. It doesn't really matter. It's going to be close enough. And for the males, I get approximately a horizontal line. Well, the interesting thing about a horizontal line means if my slope is 0, I can make no prediction because regardless of the play time, the age doesn't seem to change. So guess what? Based on scatter plots, for which gender does there appear to be evidence that more time a lion cub spends playing, the sooner the cub begins to begin hunting? For the male, I have a horizontal line, so it doesn't appear to make any difference. So it does not appear to be for the male cubs. Let's see if it makes sense for the female cubs. Well, if I spend a lot of time, 4.5 hours a day, I start at a much younger age, or if I start at 4.3, I'm at about 12 and a half months. If I only spend 3.5 hours, I'm more like 15 and a half months. So basically, as I increase my time playing, my age when I begin hunting is less. So this is for females only. As females play more, they hunt at an earlier age. Males doesn't seem to make a difference. All right. There is no prediction as to playtime and the age they begin hunting. They seem to all begin hunting around the same time, regardless how much time they spend playing. Okay, number 30. A 95% confidence interval for the mean time in minutes for a volunteer fire company to respond to an emergency is determined to be 2.8 and 12.3. Which of the following is the best interpretation of the interval? All right. And by the way, this is in minutes and this is the mean time. So if we were using our conclusion, we'd say this. We are 95% confident that the true population mean response time in minutes lies within the interval 2.8 and 12.3 minutes. All right. So 5% of the time, for 5% of the time for response is less than 2.8 or greater than 12.3. It's not 5% of the time. 5% of our intervals are wrong. So we can't make that comment because that's specifically about the time. The probability is 0.95 that a randomly selected time for response will be between 2.8 and 13.2, 12.3. We never want to talk about probability. I know they did on an earlier problem, but please don't. 95% of the time, the mean response time is between this. No, 95% of the intervals will contain it. All right, we're 95%, it lies within the interval, but we're not saying the mean times. We have no confidence in that. We are 95% confident that the mean time for response is between this. That sounds really good. Let's look at E just to make sure. We are 95% confident that a randomly selected time for response will be, we don't have anything about the time. Again, we're not talking about individuals. We're talking about the mean time. All right. I wish they had used the word population to describe it, but we're 95% confident that the population mean time or the mean real time lies within this interval. All right. So this is our best answer is letter D.